Hello and welcome to lecture 11 of the course Theory of Computation. In this lecture, we continue to discuss the equivalence of regular expressions and regular languages. In the previous lecture, we saw what regular expressions were, and then we stated this theorem 1.54, which states that a language is regular if and only if it is described by some regular expression, right? So this once proved, this will be yet another characterization for regular languages. But then there are two directions to prove. The first direction is that if there is a regular expression, the language described by that regular expression happens to be a regular language. So this proof we saw it in the previous lecture. By given a regular expression, we constructed NFA for the regular expression. So we gave a procedure to construct an NFA for a regular expression. In this lecture, we prove the other direction, that is that if there is a regular language, then we can say that it is described by a regular expression. So if you give me a language that is regular, right? So far we have not proved the equivalence. So when you say regular language, it means something that can be recognized by a DFA or NFA, right? So if you give me a language that is recognized by a DFA, for instance, right, as per our current definition of regular languages, something that is recognized by a DFA is a regular language, right? Then we can show that it is described by a regular expression. So what we will do is we'll give a way to construct a regular expression from the DFA or the NFA, right? So as many of the proofs in this course, the basic idea is kind of simple, right? But when you build it together, when you put it all together, it seems like a bit involved and complex, but the core idea is fairly simple, right? So what we'll do here is not to really explain the proof in its full detail. Instead, we'll just give the high level outline, and the main part of the proof, the core idea of the proof, that part alone we will explain in the detail. Okay. So what is required here? If you give me a regular language, then we have to show that there is a regular expression. So when I say if you give me a regular language, as per the current definition, it means that we can assume there is a DFA that recognizes that language, right? Now from the DFA, we will construct a regular expression. So this is the proof. Like this is what we need to do in the proof. How do we obtain a regular expression from the DFA that is given, right? So DFA is a automata based it's an automata, and from there how do we obtain a regular expression? That is the main non-trivial thing that we need to do. So what we will do is we will start with so because it's a regular language, we can assume there is a DFA. Then we will convert it into something called GNFA. So GNFA stands for generalized NFA, generalized non-deterministic finite automaton. So DFA will be transformed to a GNFA, and GNFA we'll keep repeatedly converting, reducing the number of states of the GNFA. So initially, let's say it has 5 states, then it will become 4, 3, 2, and finally once we have 2 states, we can obtain a regular expression from the GNFA. So we'll keep shrinking the GNFA again and again, and finally we will get the regular expression, right? So that is a very, very high level outline of the proof. Now let's go to see a bit more detail. So for instance, let us see what is a GNFA. GNFA stands for generalized non-deterministic finite automaton, right? It's an NFA, but there is some generalization going on. Let's see what it is, right? So the main thing is that, or one of the things that a GNFA has is that, think of it as an NFA, but let's say NFA, for instance, let's say between 2 states, it will have a symbol, let's say 0. On between 2 states, if there is a transition, it will have some symbol on it. Maybe it says 0, or perhaps it says 1, right? Or it may say epsilon. But in case of a GNFA, we will have regular expression. So it may say things like 0, 1 star, meaning now we can go from the let's say state Q to state R, right? when we see some member of 0 1 star. So like let's say the input we see 0 1 1 1, right? So it is 0 followed by 3 ones. So this is a part of this can be generated by the regular expression 0 1 star. So upon seeing this 0 1 1 1, we can move from Q to R. We can also move from Q to R upon seeing 0 1 1, right, or upon seeing 0 1, because they are all part of the regular expression language generated by the regular expression 0 1 star, right. So instead of having a single symbol or an epsilon on an arrow, GNFA is capable of, or in a GNFA we can have regular expressions in the transition. That is the main difference between an NFA and a GNFA, right. So that's how it is generalized. In an NFA there is only symbols from the alphabet on the arrows or the epsilon transition. Here we could have these things, we could have regular expressions, right. There is one more difference, which is that so a GNFA is written as a 5 tuple, okay, it is written as a 5 tuple, similar to what we have seen before, like it's Q sigma delta Q start Q accept. So you would have already noticed what one thing that is different here. So one thing that is different here is that Q accept seems to be the accept state. In both DFA and NFA that we saw here, in the place of Q accept we had a set called F, right. Now the notation itself is implying that the accept state is a single state, right. There is no multiple accept states, right. So this is one difference, this is a second difference, right. So difference 1 was that we could have regular expressions on the transitions, not just symbols. Difference 2 is that we have a single accept state, right, and not just a set of accepting states. And difference 3 is that the transition function, so in the case of NFA or DFA, we had delta Q cross sigma and mapping to another state or a set of states, right. But here we have here delta denotes the label that is in the transition across two states. So let's say R is one state and S is another state, and let's say this label is, let's say 0 1 star 0, okay. Let's say the label is 0 1 star 0, then this will be denoted, right. So this will be denoted by the notation delta of R comma S is equal to 0 1 star 0, right. This is what it denotes. So notice this is what we have here, right. We have that so given the beginning of the arrow, beginning of the transition, ending of the transition, we define delta to be the label of the regular expression on that transition, right. So every transition has a regular expression labeling it. So delta RS gives the, or equals to the regular expression that is labeling the transition. So this means that any member of the family 0 1 star 0 can be used to transition from R to S. The other thing to note is that R can be any state except the accepting state, right. So the first, what I mean is over here we have a Q accept here. So we can have the first state of delta RS, or the first argument of delta could be any state except the accept state. So which means the accepting state, there is no transition starting from the accepting state, right, which means there are only incoming transitions to the accept state, and there are no transitions that are like S cannot be Q start. So there are no transitions that are ending at the starting state, right. So these are the two things. So which means the starting state is, there is no incoming transitions to the starting state, and there are no outgoing transitions from the accept state, right. So which means if this is Q start, there is nothing incoming here. All the arrows would be sorry, all the arrows would be outgoing, and q accept will be the opposite. So suppose this is q accept, it can only have incoming arrows, right? So, and between any other pair of states R and S, there will be an arrow. Okay, so this will also be, maybe you may be wondering how to, like, what would be the label of, like, we are saying that between any pair of states there is an arrow and it has a label. We have to figure out what the labels are, or we have to identify what the labels are, right? So, and the argument here is from script R. Okay, so it's just a fancy R, which we say is a set of all regular expressions over sigma. Right. So this example in the black box, just keep that in mind, right? So maybe this is one that I am highlighting right now. So delta of R comma S denotes the label on the arrow from R to S, and the label is a regular expression. Right. So this is what we need to keep in mind, and this is the next sentence is whatever I have just explained. If delta of Qi comma Qj is R, capital R, where R is a regular expression, this means that you can move from Qi to Qj when you read any string that is described by the regular expression. So any string W that is described by the regular expression R. Right. So if it is 0 1 star 0, then you can make a transition if we see a string, let's say 0 1 1 0 or 0 1 0, because both of these are members of the regular expression 0 1 star 0, right? And when does a GNFA accept? This is also fairly straightforward. We have seen acceptance of DFA, NFA. It's along the same lines. It accepts a string W if you can break down W as like W1, W2, etc. Where each one of these W1, so notice that W1s are not symbols. It could be substrings. It could be a set of symbols, right? So such that you start at the starting state Q0, and so W1 takes it from Q0 to Q1, W2 takes it from Q1 to Q2, right? So this is some string, and W and so on till Wk takes it from Qk minus 1 to Qk, and Qk should be the accept state. So Q0 should be the start state, Qk should be the accept state, and each of these Wi's take it from Qi minus 1 to Qi. In other words, what is the condition that has to be satisfied for Wi to take it from Qi minus 1 to Qi? The label on this right, Qk minus 1 to Qk, sorry, the label of this Qi minus 1 to Qi, right? If Wi has to take it from Qi minus 1 to Qi, let's say is a regular expression Ri, right? This Ri should describe a language that contains Wi. So that is what I have written here. Wi should be a member of this language described by the regular expression Ri. Right. So basically, we should it's exactly like an NFA, but the one difference is that the accepting state is unique. In an NFA, there are multiple accepting states, and then the breaking down of the strings in an NFA was symbol by symbol or maybe sometimes epsilon. Here, the breaking down could be elements of sigma star, which means substrings could be part of the breaking down. You start at the start state, you end at the accept state, and each substring Wi should take it from Qi minus 1 to Qi, right? Which means that the label of that arrow, let's say it's Ri, should describe a language that includes Wi, right? So that is basically what is a GNFA. So GNFA is a construct or a concept that we will use only for this particular proof. So after this proof, we will not be using this notion of GNFA. Okay, so hopefully GNFAs are clear. So right, and let me now explain how the proof will operate. So remember, we have to show that any regular language has a corresponding regular expression or an equivalent regular expression. So given a regular language, we may assume that we are given the DFA corresponding to the regular language, right? Because that's the definition of regular language. So for instance, let's say that the language A, let's say the language is A. Suppose it has a DFA that contains 6 states. Okay, 6 states DFA. So this is just an example. Now we can easily convert it. Okay, so this I will just describe. I have not written down, but I will just describe. We can convert this DFA into an 8-state GNFA. So from 6-state DNFA, we can go to an 8-state GNFA. So 6 to 8 meaning we just add 2 states. That's how we go from 6 to 8. So we just add 2 states. Now then thereafter what we do is we successively reduce the number of states. So from 8-state DNFA we will go to 7-state GNFA, from where we will go to 6-state GNFA and so on, 6, 5, 4, 3, and finally we will reach a 2-state DNFA. Okay. So what is a 2-state GNFA, right? So GNFA already has, if you recall, a designated start state and a designated accept state, right? So the 2-state GNFA must have a start state and accept state, and they have to be 2 different states, right? Because start cannot be the same as accept, because the arrows there can only be outgoing arrows from start and only incoming arrows to accept, right? So this is what we said earlier. So which means that the 2-state GNFA, right, can only look like this. So this is how a 2-state GNFA can look. So the first state is a start state, and the second state, the state by the right side, is an accept state, right? So this is start and this is accept, right? And it is labeled by some regular expression, right? Because there is only one arrow to be drawn. If there were 3, there could be multiple arrows, but now we know that from start state there can only be outgoing, and accept state there is only incoming. So there is only one arrow to be drawn, which is from start to accept. And let this be labeled by some regular expression, let's say R. Now it's very clear what is the language that is accepted by this GNFA, which is of 2 states. So the start state, from the start state you need to go to the accept state, and which are the strings that will take you from start to accept? The set of strings that are described by the regular expression R, right? So now for this GNFA, the equivalent regular expression is simply R. So the set of strings that this GNFA accepts is exactly the set of strings that are described by the regular expression R, right? So for a 2-state GNFA, we know what is the equivalent regular expression, right? So the 2-state GNFA, we can say that R is the equivalent regular expression, right? Now what we do is we start with the DFA, 6-state DFA, let's say, we make an equivalent 8-state GNFA, and then from 8-state GNFA we move to an equivalent 7-state GNFA, to a 6-state GNFA, and so on till we reach an equivalent 2-state GNFA. So whatever was recognized, whichever language was recognized by the original DFA, the same language will be recognized by the 2-state GNFA. But for a 2-state GNFA, the language, the equivalent regular expression is immediately clear. What is the regular expression? So it's just, there is only one transition arrow. You look at the label of that arrow. That regular expression is the equivalent regular expression. So that's how we go to the equivalent regular expression of the original DFA. Right? So we start from the some state DFA. We move to a GNFA by adding 2 states. Then we will describe how to reduce states one by one from the GNFA till we have just 2 states. But when we have 2 states, the equivalent regular expression is clear, right? So that is the way the proof will operate. So there are 2 things here, right? Initially you are given a DFA. How do we go to a GNFA? By adding 2 states. This part, so let's say there is some DFA given. So let's say this is the start state. There could be multiple states, and there could be, let's say, 2 accept states. This is a DFA. Now how do we move to a GNFA? there could be multiple arrows here, right? So there could be arrows going many ways, right? How do we move to a 6-state DNF? 6-state 8-state GNFA. Now we cannot make. So now notice that there is one issue is that the DFA, there are arrows going into the start state, right? There are arrows going into the start state, which we don't want in the GNFA, because we can only have outgoing arrows from the start state, and there are arrows coming out of the accept state, which also we do not want in the GNFA. So what we do is we add a new start state. Maybe I'll make it a new color, right? So this will be the new start state, and make an epsilon transition to the old start state of the DFA, and we make a new accept state, right, which again I am making red color. So this is the lone accept state, and we make epsilon transitions from the existing original accept states to the new accept state. So now there is only outgoing arrow from the new start state and only incoming arrows to the new accept state. Now there are issues like in a regular DFA, we may not have all kinds of arrows possible, right? But then the GNFA requires that for every pair R comma S we need to have a label. So what we do is, let's say if there are basically for those, let's say this arrow, let's say this arrow is already labeled 1, let's say some symbol 1, then 1 continues to be the label. Now if there is no label, then you basically add a arrow. Let's say now there is no label from here, right? There is no label. So you add an arrow with a empty set, meaning there is nothing that can take you from that state to the nothing that can take you through that transition in the original DFA. So when there is no transitions possible, you just add an empty transition, right? So that is how we go from a 6-state DFA to an 8-state GNFA, or any k-state DFA to a k+2 state GNFA. This is the first step. Basically you add a new start state, you add a new accept state, connect them with epsilon, and then wherever there are no transitions available, you label them with the empty set. Now the next part, so this is the first part of the proof, which is, I'm not going into details, but it's fairly clear. The second part is how we go from a k-state GNFA to a k-1 state GNFA. Right? How do we reduce one state of the GNFA? This is what I want to describe next. This I will do it in a bit of detail, right? So this is the key or main idea of the proof, where we reduce the number of states in GNFA by 1. So what we want to do is, let's say basically what we do is we identify one state that we want to remove from the GNFA. Let's say it is this highlighted state. I am calling it Q rip, right? So I want to just rip off that state from the GNFA. So now how does it impact the GNFA, right? So basically earlier you could go from Qi to Qj by seeing a symbol or a string from R4. You could also go from Qi to Qj by seeing a string that is from R1 concatenation R3. Right? R1 concatenation at R3 means a string from R1 will take it to Qrip, and a string from R3 will take you to Qj. Right? So you could go from Qi to Qj through R1 R3 also. You could also go from Qi to Qj by processing a string R1 R2 R3, because you could go from Qi to Qrip, R2 will keep it at Qrip, and then R3 will take it to Qj. So you could also go from Qi to Qj by seeing a string from R1 R2 R3, a concatenation of 3 regular expressions. Could even be R1 R2 R2 R3, right? So the first string from R2 keeps it at Qrip, the second string from R2 also keeps it at Qrip, and then you go from Qrip to Qj. So it could be multiple times. So we may not use any instance of R2. We may use one instance, two instances, or many more instances. So the key thing to note here is that, in summary, what we want to say is that any string that is from this particular regular expression, right? So basically R1, R2 star, R3 will take you from Qi to Qj through Qrib. And now that Qrib is removed, we need to preserve this information. So we will include that in the arrow from Qi to Qj. So in the arrow from Qi to Qj, we want to add this information, that R1, R2 star, R3. But then whatever was already there, we are not going to lose that. So we want to retain that as well. So what was earlier there, R4 was an existing label of Qi to Qj, that we will preserve. So now any string from R1, R2 star, R3 union R4 will take you from Qi to Qj in the red GNFA. But now in the green GNFA, we don't have the state Qrib. So we will include that in the label from Qi to Qj. So this is the main idea. So this basically indicates if a state is removed, so the removed state being Qrib, what should be the change in the labels of the other states. Right? So how to relabel the other states if a certain state is removed. So this is how you relabel. So basically, if you want to remove Qrib, you look at, for any pair Qi Qj, you see what is the arrow from Qi to Qrib, Qrib to itself, Qrib to Qj, and then notice what is R1, R2, R3, R4, etc., and then use that to label the new arrow from Qi to Qj. We need to do that for all the pairs Qi Qj, right? In both the directions. So for Qi Qj we identified the labels. For Qj Qi also we will have to identify the appropriate labels. And even in the state like Qi to itself also we will have to identify the appropriate labels, right? Because from Qi there would have been a self loop, but then you could go from Qi to Qrib and then Qrib to Qi. So in general, let me just say Qi to Qj. So this yields the following procedure, right? It's a recursive procedure, right? So which talks about how to convert G. Let's say G is a GNFA, right? G is a GNFA, and we want to convert G is the GNFA. We want to convert G from k states to k minus 1 states, right? And we want to keep doing that till we get to 2 states, right? So if k is 2, then we know there is only one transition, and that the label of the transition will be the regular expression that is desired. If k is more than 2, what we will do is to reduce one state. So what do we do? Then we identify a state called Qrib. It could be any state except for the start or accept. And what we do is, for all the pairs of all the other pairs Qi Qj, we do the transformation that we just described here. Right? So basically, you remove Qrib, you relabel the arrow Qi to Qj with R1, R2 star, R3 union R4. So what we do here is, this is described very briefly. We move from G to G prime. So G prime is a new GNFA. It contains the same alphabet, or it operates on the same alphabet sigma. It contains the same starting and accepting state as G. Two things change. One is the set of states. Set of states, from Q you remove Qrib. So Q prime is Q, this is set difference. So this is the same as Q minus Qrib. So it's all the states that was in G except Qrib. Right? So this backslash is another way to denote set difference. And the other thing is delta prime, right? From the transition function changes. So if for any Qi Qj which are in the new machine, meaning if Qi, as long as Qi and Qj are not the Qrib, we identify what is R1, R2, R3, R4 based on the connection with QRIP, and then we relabel it with R1 R2 star R3 union R4. So earlier the earlier label would have been R4, right? So now we add using union R1 R2 star R3, where R1 is the label from QI to QRIP, R2 is the label from QRIP to itself, and R3 is the label from QRIP to QJ. So this will ensure that we get an equivalent GNFA. So meaning G prime will be equivalent to G. Any string that was accepted by G will continue to be accepted by G prime and nothing more. And now that so basically we have reduced one state, we have removed QRIP. Now we can do the same thing again. So now we check whether basically what we do is we make a recursive call of convert G prime, right? So recursive call to convert G prime, meaning for G prime we do the same thing. So we check whether it is 2 states, if so return R, otherwise we do the whole thing again. You identify new state to remove, and so at some point you run out of states and we end up with a 2-state GNFA, in which case it's clear what is the regular expression. So hopefully the outline is clear. We move from a DFA to a GNFA with 2 more states, right? And then we successively reduce the number of states by 1 by 1 by 1 by 1 till you get a 2-state GNFA. And in a 2-state GNFA there is only one transition arrow, and that transition arrow contains some regular expression, and that regular expression is the equivalent regular expression for the current GNFA and for the previous GNFA, and finally to the DFA that we started with. Right. So now one very small proof, since we didn't do much of detail. This is a claim in the textbook. It's presented as a claim as part of one of the proofs. So what it's claiming is that convert G is equivalent to G, meaning convert G is the result of this process. So meaning it's a regular expression given a GNFA, a k-state GNFA. It claims that the convert G it gives you a regular expression which is equivalent to the GNFA G, meaning whatever string is accepted by or accepted by the GNFA G is described by the regular expression, and vice versa. So the proof is it is just an inductive argument. If G has just 2 states, this is true by the definition of the GNFA, right? Because there is only one arrow. If G has more than 2 states, right? So if k greater than 2, then what we have to show is that we will just show that G will be transformed to G prime by reducing one state. We will just show that G prime is equivalent to G, and then inductively it follows G prime is equivalent to the next one, G prime prime or something, and so on till we get a state of a GNFA of 2 states, at which case it is true by the base case of 2 states. So for now we will just focus on this claim that G prime is equivalent to G. This is what we want to show, meaning the exercise of removing one state preserves the language recognized by G. So we will do something very simple. Suppose G accepts some string W, we will show that G prime also accepts the same string, right? So suppose G accepts W. Now let us say that in the process of accepting the string, it goes from the start state, let us say to Q1 to Q2 and so on till Q accept, right? And what we want to say is that G prime also accepts the same string. So suppose QRIP is not in the above sequence, Q start, Q1, Q2, this does not contain QRIP, in which case it's fine, because for any pair, let's say Q1, Q2, there was some transition, right? The new Q1, Q2 also, it contains the existing transitions, right? Because this is the transformation, right? QI, QJ remains QI, QJ, but the label R4 was replaced by R1, R2 star, R3 union R4. So any string that could take you from QI to QJ earlier can still take you from QI to QJ, because any string that could take you from QI to QJ earlier was described by R4. Still R4 is that is part of this regular expression. So, all the strings that are part of R4 can still take you from Qi to Qj, right. So, if Qrip is not in the above sequence, all the transitions remain in G and are valid transitions, right. Hence, G prime, okay, maybe I already written that, hence G prime also accepts W. Suppose this sequence contains Qrip somewhere, right. Just for sake of simplicity, let me say that Qrip appears between some two states in the sequence. Let us say the two states were Qi and Qi plus 1, right, these two states. And Qrip, let us say it appears more than once, let us say Qi, then Qrip again, then Qrip once again before Qi plus 1. So, now if you notice the arrow from Qi to Qi plus 1 now would have been replaced by R1 R2 star R3 union R4, right. So, where what is maybe I will just use a different color. Let us say this is Qi, this is Qi plus 1, this is Qrip, right. So, this is R4, this is R1, this is R3 and this is R2. So, now if there was this was the earlier, suppose this was the earlier sequence of states. Now, we used R1 to go from Qi to Qrip, we used R2 to remain in Qrip and R2 again to remain in Qrip, and then R3 to move to Qi plus 1. So, R1, R2, R2, R3 was used to move from Qi to Qi plus 1. Then now in the present GNFA, the label is replaced by the Qi to Qi plus 1 label is replaced by R1, R2 star R3. So, R1, R2, R2, R3 is still part of this regular expression. Hence, the same string can be accepted even though Qrip is not there, no longer there in the GNFA, even then this string is accepted as part of the transition from Qi to Qi plus 1. So, this shows that whatever be the situation, whether Qrip features in the sequence or it does not, the converted GNFA G prime will still accept the string W. So, what we showed is that if G accepts the string W, G prime also accepts, and the same reasoning can be used in the opposite way. If G prime accepts, then it has to be either using R1, R2 star R3 or through R4, in which case it is, in either case it is there is an equivalent transitions in the G as well. So, G prime and G are both recognizing the same set of strings. So, this we showed that this shows that G prime and G are equivalent, and you can use the same argument again and again and use mathematical induction. So, G prime is equivalent to the, let us say, G double prime where one more state is reduced, and so on till we get to the final two state GNFA, right. So, that the final, let us say, two state GNFA, maybe we call it G0 or something, or G2 or something, right. So, G2 has these two states, and then it is immediately clear what the equivalent regular expression is, right. So, at that stage it is very clear what the regular expression is, and that will allow us to tell what the equivalent regular expression R is, right. So, that is how we move from a DFA to an GNFA and then successively reducing the number of states while preserving the language recognized, and finally we reach a two state GNFA, and then the two state GNFA will tell us the regular expression that is equivalent. So, I will just quickly summarize. The goal of this lecture was to show the complete the proof of this theorem, which was that a language is regular if and only if some regular expression describes it. In the previous lecture, we already saw that if we have a regular expression describing some language, it is regular. So now our goal is, if a language is regular, we should have a regular expression describing it. So suppose the language is regular, which means there is a DFA that recognizes that language. We add two states, a new start state and a new accept state, and we add empty set transitions to all the other places to get a new GNFA, which is clearly equivalent, right? So we are not adding anything, and from that GNFA, so basically if you had a 6-stage DFA, we will get an 8-stage GNFA, and from that GNFA we successively reduce the number of states, right? So by doing this operation again and again, so we pick a state which is not a start or accept state, we remove it by relabeling the other arrows. So for all the pairs Qi Qj, we relabel it by seeing what is Qi to Qrib, Qrib to itself, and Qrib to Qj. This needs to be done for all the pairs, right? Even the pairs Qi Qj we have to do in both order, and also the pair Qi Qi, right? And this will give us a equivalent GNFA but with one state less, and we keep doing that till we get a 2-state GNFA, right? So a 2-state GNFA will be of this form, right? It has just a start state and accept state and just one transition labeled by a regular expression. So for this 2-state GNFA, the equivalent regular expression is trivial. It is just the label of that one transition, and that completes the procedure of how we can get the regular expression for any regular language. So from any regular language, you start with the DFA, then move to the GNFA, and then successively reduce the number of states till we get 2-state GNFA, and that tells us how to get the regular expression. And with this, we have completed the proof that right. So this completes the proof that regular expressions are another way to characterize regular languages. So now the proof is complete. This shows that given any regular language, there is a regular expression. So to show that a language is regular, we have a third way now. So the earlier two ways was that you provided DFA or you provide an NFA. Now one way to show, a new way to show a language is regular is to provide a regular expression for it, right? So so this can be quite useful. So if you are asked to show that a certain language is regular, instead of building a DFA or an NFA, we could just we could just construct a regular expression that characterizes that language, right? So that with that we complete week 2's lectures, right? So just to quickly summarize, what all did we see? We saw non-deterministic finite automata. We saw that we could prove these are equivalent to deterministic finite automata. We saw that we could use the NFAs to prove the closure properties, that is regular languages are closed under union, concatenation and star, and then we explained regular expressions, and we showed that the regular expressions are also yet another equivalent representation for regular languages, right? So that completes week 2, And so we have regular languages that we have already seen, and 3 different characterizations for it. Now what we will move on to is languages that are not regular. So one may wonder, is everything regular? Can we represent all the languages using a DFA or an NFA or a regular expression? The answer is no, and you'll have to wait till the next week's lectures to see some examples for that. Okay, thank you.